Did you miss class today? Well, you're in luck because I got a whole video on what complex roots are. All right, so let's start with the refresher and imaginary numbers. So we know that 2 times 2 is 4, and we know -2 times -2 is 4. But what times what will give us a -4? And that's when our imaginary number comes into play. So I squared equals -1. Or you can just rewrite it as I equals square root of -1, which we know these two are equivalent. So in words, imaginary numbers, when squared, gives a negative result. So, for example, if we have the square root of -9, think about it. What would we do? So we could rewrite this as redo. 9 times -1. And then we could simplify this down to 9 times the square root of -1. So we know the square root of 9 is 3 times, and then now we know our imaginary rule, the square root of -1 is I, so I. And then we could say this is 3I. All right, so now we're going to talk about the powers of I. So we're going to go through each one and see if we notice a pattern. So we know that I equals the square root of -1, which just equals I. Then we go on to I squared, and we also know that's equal to -1. But what do we do when it's I cubed? Well, we can just split that up into I squared times I, which we know I squared equals -1, and I just equals I. So -1 times I equals -I. So then I to the 4th, we once again split it up, and this time we do I squared times I squared. And we know I squared once again equals -1. So we just do -1 times -1 equals 1. And we keep doing that for each process. And if you take a look at the pattern, we notice that there's a cycle, and it's going to end up being in a circle. So we're going to go over to graphing imaginary numbers. It's not that hard. It's basically like the coordinate plane, but this time it's our complex plane. We have imaginary numbers on the y-axis, and then we have our real numbers on the x-axis. So let's start with x squared. So right here we have a real number, but we don't have an imaginary. So we have -1. So we're going to go over -1 on our real plane here, -1, and then up 0 because we don't have an imaginary number. And then if we go to I cubed, we just know that equals -I. So we're going to go down -I, but we don't go over any because there's no real number. And then for I to the 4th, we know that equals 1. So we'll just go over 1 on the real line. And you'll notice that there's a little cycle, and it's going to keep going no matter how far up we go. All right, so now we know what an imaginary number is and a real number, but what do you get when you combine them? So when you add a real number and an imaginary number together, you get a complex number. For example, down here we have 3 plus 5i. Our real number is a 3 and our imaginary number is a 5. Whenever you're adding these, you would think maybe this could become 8i, but you can't combine an imaginary with a real number. You have to leave it in this form. So, like I said, a real number plus an imaginary number makes a complex number. So going back to our graph of the complex plane, like we did the last video, you can see that we have this labeled, our imaginary numbers on the y-axis and our real numbers on the x-axis. So, for example, let's start with 3 plus 5i. So we go over 3 on the real x-axis, and then we go up to 5i, and that's our point. Same goes for 2 plus 3i. We're going to go, or -2 plus 3i. We're going to go over -2 and then up 3i, and we plot that. So now that we know what a complex number is, I want us to make the realization that sometimes a quadratic equation might have a complex solution, which we will call a complex root. So let's say you're given the problem 2x squared minus 8x plus 10. It's not going to be that easy to factor. So as we recall, we're going to use the quadratic equation. So that's just negative b plus or minus the square root of b squared minus 4ac all over 2a.
The quadratic formula is negative b plus or minus square root b squared minus 4ac b squared minus 4ac all over 2a all over 2a.
So going back to our equation, we're going to plug it in. So we have 8, which our negative cancel because we have negative 8 and negative b, so it's just going to be 8. So 8 plus or minus the square root of negative 8 squared minus 4 times 2 times 10 all over 2 times 2. If you don't understand that, maybe pause the video and see how I got from here to here using the quadratic equation. Okay, moving on, we're going to simplify what's underneath the square root. So we have 64 minus 80. And then we keep simplifying what's under the square root, and we have negative 16. So this is when our imaginary number rule will come into play. So if you come up here, we're going to make that negative 16 under the square root. We're going to make it 16 times negative 1. And if we use our imaginary number rule, we know negative 1 just equals I. And then the square root of 16 is 4. So that will simplify to 4i. And then we have this all over 4, and we can simplify that. 8 divided by 4 is 2, and 4 divided by 4 is 1. So our final solution is 2 plus or minus I.
So now that we have our solutions, let's graph the equation. So we have 2x squared minus 8x plus 10. So from this, you're probably wondering where our roots are because it looks like our equation doesn't touch the x-axis. It crosses the y at 10, but it doesn't cross the x-axis, and we're used to seeing our roots crossing the x-axis. So let's take a look and see how we get those. So now we're going to take a look at this picture. So the red parabola you see is what we originally graphed, our equation, the 2x squared minus 8x plus 10. So as you can see, the green parabola is they just reflected over the x-axis. And the circle, if you recall, when we did the powers of imaginary numbers, it created a circle. So let's just view this plane as our complex plane. So our solutions, we got 2 plus or minus I, which is 1I. So what we did was we went over 2. So we went over 2 because our real number was 2, and then we either go up 1 for the complex number, or we also go down 1. And then that creates that circle because of the powers of imaginary numbers. So then you can see where our complex roots would cross the x-axis at 1, 0, and 3, 0.